Hi everyone. In this section, chapter 7, section 3, we are going to talk about logarithms. And logarithms are something that I haven't taught you before, depending on where you come from. I don't know if you know anything about them, but let's look. They are the coolest things, and once you get a hang of them, they're super, super helpful. So a logarithm, in order to understand logarithms, they're very much related to exponents. So I want to kind of review what an exponent is. If I have a base, and if I have a base to the power of x, this base is my growth rate, right? So I have, let's say, if my growth rate is 2, then something is doubling every so often, every time, whatever that term is. If it's every day, week, month, year, whatever, and my base is 2, then that's how many times that growth rate occurred. That gives me my answer. Now in a logarithm, we're basically looking at an exponential equation, but we're looking at them in a different way. Here I have my base to this many growth rates leaves me this amount, right? So in a logarithm, what happens is this base comes over here and my answer is the exponent. So my log, and I actually add the word log, so I know that that's what happens. So you can almost picture it in your mind that I take a giant log and I grab a rope and I grab this base and I jerk it with the log and I swing it over here. Here's my log that's attached to it. It hooks that base, puts it down below because it's my base, and hook brings it over here with the y. And notice now my exponent becomes the answer. So when you have a log problem, your answer is the exponent. Let's look at this with numbers. Let's say that our y is 8 and this is 2 to the power of 3. So 2 to the power of 3 is 8, right? If I grab my log and sling this over here, so log base 2 of 8, notice my base is now here below the 8, equals what's left behind is my 3, correct? Which basically means 2 to what power gives me 8? You see? And my answer is 3. How many times do I double, or how many 2's are in 8? Sort of like that. How many doubles are in 8? That's kind of an, except it's not division, it's to the power of. You see, how many times have I doubled to get 8? The answer is 3. Let's practice working with this. What I want you to get the feel of is how I can change an equation from an exponential model to a logarithmic model. And so if you really think about tying a log in and swinging it to the other side, the base swings back and forth. This number here and the exponent stay, it's the base that moves. So if I grab a log and swing it over here, I'm going to have my log base 10, and that's written as a subscript, and that's how you say it. Log base 10 of 100, and that's on the same level as log. Do you see that? Equals 2, which basically is 10 to what power is 100? And it's 10 to the power of 2 is 100. So here it is in exponential form. Here's the same thing in logarithmic form. 81 is 3 to the power of 4, isn't it? What would this look like written as a logarithm? So lasso that base with your log, whip it to a log, and sling it over to the other side. So it's going to be a base below 81. And log base 3 of 81 equals, and my 4 is left there. 3 to the power of 4 is 81. 3 to what power is 81? The answer is 4. I want to do a few more of these. Sometimes it helps to just take a piece of paper and do it yourself several times till you get the hang of it. 36 is 6 squared. Change this to logarithmic form. So grab that log, sling that base over to this side. Log base 6 of 36 equals my exponent. My exponent is always my answer in a log problem. Log base 6 of 36 is 2 because 6 to the power of 2 is 36. What do you do with fractions? Are they any different? They're not any different. Here's my base. I'm going to swing that over here with my log. So grab my log, tie it onto that base, swing it over. Now I'm just going to put 2/3 down there as my base. 2/3 of 8/27 equals 3. Notice I don't need the parentheses anymore either, do I? 2/3 to what power is 8/27? It's 3. Oh, 3 to the power of 0 equals 1. Now what do we do? Same thing, right? Take the log, grab my log, tie it on, sling the 3 down. 1, log base 3 of 1. By the way, any base of 1 is going to have what is its exponent? Those, hopefully you will be able to recognize. Once you see any base to the power of 1, you know this is going to be a 0. Now we're going to evaluate logarithms. Okay, now we're going to find out what is that power. For instance, log base 8 of 32. What is that value? That equals what? 8 to the power of what is 32? And that's kind of tricky to think about. So what we're going to do to help us is we're going to change this from logarithm form to exponential form, and here's how. Now we're going to go the opposite direction. I'm going to take some little dynamite, I'm going to blow up that log, and it's going to release the 8, and the 8's going to sling over to the other side. So what happens is the 32 is left behind. By the way, I'll do that to help us. And that becomes 8 to the power of x. Now you still may be thinking, well, how's that supposed to help us? Because 8 squared is 64 and this is 32, so that makes no sense. But if you notice, both of these can't have a base of 2. For instance, 8 is 2 to the power of 3, right? 2 cubed, I'm going to put 2 cubed in place of 8. And 32 is 2 to the power of 2, 4, 8, 16, 32. 2 to the power of 5. So since I have 2 to the power of 5 and 2 to the power of 3 raised to the power of x, by the way, what happens if I have a power of a power? So this becomes 2 to the power of 3x, right? Since my bases are now the same, all I have to do is make my exponents the same. 5 equals 3x. 3 times x has to be 5. So to solve for x, I divide by 3, and I get that my x is 5/3. Log base 8 of 32 is 5/3. You might think, wait a minute, how could that be? Well, look, think about it. Remember when we dealt with exponents? The cube root of 8 is 2, and 2 to the power of 5 is 32. It works, but it was also a crazy hard way to start. So let's start with a few simple ones that aren't even in your book. I'm just going to help you out here. What's the value of log base 3 of 27? Which basically means 3 to what power? If I rewrite it this way, 27 is 3 to what power? The answer is 3. So the value of this is 3, because 3 to the power of 3 is 27. Remember, in a log problem, our answer is the exponent. Okay, what's the value of log base 2 of 16? Which means 2 to what power is 16? 2, 4, 8, 16. It's 4. The value of this is 4. Remember, your answer is the exponent. Evaluate log base 5 of 125, which means 5 to what power is 125? 5 to the power of 3. So the value of this evaluated is 3. Log base 4 of 32, let's evaluate that. Again, 4 squared is 16, and 16 times 4 is 64, so I cannot use the 4. So what I'm going to do, I'm going to switch it. 4 to the power of x equals 32, and I'm going to change both of those to base 2 again. So 4 is 2 squared, to the power of x, and 32 is 2 to the power of 5, 2, 4, 8, 16, 32. So now 5 has to equal 2x, divide by 2, and I get x equals 5 over 2. That makes sense. The square root of 4 raised to the power of 5, sure enough, would be 32. So our answer is 5 over 2. By the way, if you're pushing that log button on your calculator and going, why doesn't this work? Because your calculator will not give you these answers. I'll show you what that log button is for, but it won't help you with these at all. This one looks crazy. Log base 64 of 1 over 32? Oh my goodness! How are we going to do this? Let's do the same thing we did before. Let's go 64 to the power of x is equal to 1 over 32. And now I'm going to go ahead and base 2 both of these. So 64 is 2, 4, 8, 16, 32, 64. It's 2 to the power of 6. So this is 2 to the power of 6 raised to the power of x. That's this. And this is 1 over 2 to the power of 5. Let's make this negative and bring it up. There we go. So for negative 5 to equal 6x, you get negative 5/6. Negative 5 over 6. Oh my. So the negative makes it into a fraction. This means the 6th root of 64, which is 2, raised to the power of 5, but the negative flipped it, and that's why it's 1 over 32. Another challenging one. Okay, there are two kinds of logs that are used a lot. One of them is the common log, because we use it commonly. It's commonly used, and that's where we have a base 10. So if I have just the common log, it would be log base 10 of whatever. And since it's a common log, we don't even write the number 10. So if you see log x with no base, then you know it's the common log, and the unwritten number, the unwritten invisible base there, is always a 10. So if you just see the word log, which is why that log button didn't work in your calculator, it's a base 10. We use these kind of numbers when we have a range, a huge, gigantic range of numbers. Often instead of writing the numbers, which would be just too cumbersome, we use the logarithmic form. We use their logs or their powers of 10. We do this in pH numbers. We do this in decibels. We do this in earthquake magnitudes. These are all logarithmic numbers. Let me show you how this works with earthquake magnitudes. So our energy is the energy released. That's the amount of energy at 0. At 1, it's just the amount of energy released times 30. Each time you go up, so it's magnitude 2 on an earthquake, it's times the energy released times 30 squared. So you're multiplying times 30 every time. So this is 30 cubed, 30 to the 4th power. Do you see how exponentially these numbers get huge in a logarithmic scale? Okay, we can compare earthquakes, see how many times more power or more energy was released from one earthquake to another using this basic formula. So if I have this intensity, by the way, I is the intensity and the amount of energy released that you would see on a seismograph. This M stands for the magnitude that it was designated. So if I take the common log of the first intensity divided by the second intensity, in other words, I want to know the one compared to the other, how many times greater one was, so I'm dividing. What I do is I take the common log of that is the magnitude of the first one minus the magnitude of the second one. This looks really complex, but when you see it filled out and used, it's not so hard. We're going to compare two earthquakes, and we're going to find out how many times more powerful one earthquake was than the other. Okay, so I have two earthquakes that look really close together. One is a magnitude 9.3. By the way, these are real earthquakes we're talking about. The other huge one was a magnitude of 8.7. How many times greater was this earthquake than that one? Which basically means I take this intensity and I multiply it by what to get that intensity. So, subtract them. What's 9.3 minus 8.7? It's just 0.6, right? So I have the common log of this is 0.6. Now, what's my invisible base? My invisible base is 10. Remember, this is the common log. So what I'm going to do to solve for this value, to solve for this, is I'm going to get rid of this log. Remember, I'm going to blow it up, and this 10 is going to come over here, and the difference in magnitudes is 10 to the power of 0.6. That's what I put in my calculator. Not my calendar, good grief, in my calculator. So put 10 to the power of 0.6, and you will get about 4, which means this is 4 times more powerful than that. Just hard to believe, but it is. Here's your lesson check question for this section, because we are definitely dividing this in half. We're just doing, this is going to be it. Your lesson check is there's 2 earthquakes. One was 8.0, one was 6.8. I want you to tell me how many times more powerful was the 8.0 earthquake than the 6.8. So use this formula, walk through the process that I just did, and see if you can tell me how many times more powerful was the 8.0 earthquake than the 6.8. That's your lesson check. And then next time we will finish this section, just this one section on logarithms.